Identifying exactly where numbers cluster on a line requires more than visual intuition. It requires a proof of accumulation. Mathematicians use point set topology to solve this, replacing the visual idea of clustering with a formal algebraic definition. This definition relies on a specific type of coordinate, the limit point, also known as an accumulation point. For a coordinate to be a limit point, every possible neighborhood drawn around it, no matter how small the radius, must capture points from the set. On this real number line, we can draw a delta neighborhood around a central point, alpha. Inside this radius, we find a collection of subpoints. The criteria is specific. Even if we ignore the central point alpha, the neighborhood must still intersect the set at some distinct point. This formula describes that intersection. When the center is excluded, the neighborhood must contain elements of the set. Because the real line is dense, meaning there's always another number between any 2 points, the existence of even one distinct neighbor within a radius implies that an infinite number of points are gathering there. By collecting every limit point of a set into its own group, we create a new structure, the derived set, or S'. Mapping the derived set allows us to distinguish between sets that are made of isolated points and those that form a continuous density. We can test these rules by evaluating discrete sets, where points are separated by empty space. Consider a finite set containing only the integers 1, 2, and 3. These 3 points sit at fixed coordinates on the line, clearly separated from one another. To test if 2 is a limit point, we center a neighborhood there and begin shrinking the radius. As it shrinks, it eventually becomes smaller than the distance to the next integer. It captures 0 other elements from the set, failing the limit point criteria. This logic also applies to the set of all natural numbers, an infinite but discrete set. Because there is a fixed gap of 1 between every natural number, we can always find a neighborhood small enough to exclude all neighbors. Consequently, finite sets and discrete infinite sets have no limit points. Their derived set is empty because their points are mathematically isolated. Next, we test dense sets, such as the rational numbers and the entire real number line. The set of rationals, or Q, fills the line in a way that discrete integers do not. Rational numbers are dense. Between any 2 fractions, you will always find another fraction. Even as we zoom in on a microscopic neighborhood, we never find a gap. The space remains occupied by an infinite number of subpoints. Shrinking a neighborhood around any rational number will always capture infinitely many other rationals. This is true for every coordinate on the line. The neighborhood is never empty, no matter where it is placed. Because every real number acts as an accumulation point for the rationals, the derived set of Q is the entire real number line. Our third test involves the sequence 1/n, which demonstrates how sets cluster toward a specific limit. As the denominator n increases, the resulting fractional values 1, 1/2, 1/3, and beyond move progressively closer and closer together in space. On the number line, these points compress as they travel left, crowding together as they approach 0. While the sequence points get arbitrarily close to 0, 0 itself is not a member of this set. We can test if 0 is a limit point by centering a neighborhood there, even though the coordinate is outside the set. When we draw a neighborhood around 0, the right half of that radius traps the infinite tail of the sequence. Because the sequence continues forever, any neighborhood around 0 will contain terms like 1/1 billion or 1/1 trillion. This confirms a limit point is defined by spatial proximity, not set membership. A set can accumulate toward a point it does not actually contain. For this sequence, 0 is the only coordinate where points infinitely cluster, making the derived set a single point, 0. Finally, we examine continuous intervals to see exactly how strict mathematical boundaries affect the underlying laws of point accumulation. Take an open interval from A to B. In this set, the boundary points are specifically excluded. We must determine if these excluded boundaries still function as limit points for the interval. If we center a neighborhood on boundary A, the left side is empty, but the right side overlaps with the interval. That overlap contains an infinite number of points from the set. The neighborhood is never empty of set elements. This satisfies the limit point rule. It applies whether the interval is open, closed, or only closed on one side. Because boundaries always facilitate this overlap, The derived set of any interval is the closed interval from A to B. Accumulation occurs at the edges regardless of inclusion. Understanding limit points also requires distinguishing them from a similar concept, the adherent point. An adherent point has a lower requirement. Its neighborhood only needs to contain one point from the set, which can be the center itself. The difference is in the exclusion. Adherent logic only asks for an intersection. Limit point logic requires an intersection with a distinct neighbor. In a finite set of 1, 2, and 3, an adherent neighborhood around 2 succeeds by containing 2 itself. But for the limit point rule, the center is ignored. Excluding 2 leaves the neighborhood completely empty, meaning the rule fails. This means all limit points are adherent, but isolated points can never be limit points. Point set topology uses these definitions to categorize mathematical structures based on the density of their accumulation.